Molecular Geometry Practice Part 5. This is the fifth part and the final part. You should, if you don't already, know how to do this by the end of this particular part. Let's begin as if this is the first part. Formula of particle, that's what you start with. Approximate shape, total valence, total bonded electrons, total outer atom electrons needed to complete the valence. Show how the balance of the electrons are calculated. Conclude the totals, sockets, bonded electrons, and non-bonded electron pairs. Draw the final shape and include any non-bonded electron pairs. Calculate and insert the dipole moments. Determine the polarity. Draw a conclusion regarding bond angles if they are distorted due to asymmetry. Make a model using clay and toothpicks for each particle in the practice problems. I will check your progress during the experiment. Okay, 21 to 25. Ammonium, plus one charge, polyatomic ion. Ammonia, yes, it's related. Krypton difluoride. Xenon hexafluoride. And then xenon dioxide, difluoride. Let's begin with NH4 plus one charge, a polyatomic ion called ammonium. Here we have it. Approximate shape. Plus one charge. Don't forget to subtract off one electron. So you have 5, 1, 1, 1, 1, delete 1. That gives you a total of 8. 4 bonds times 2, that is 8. Hydrogen does not need any additional electrons to complete the valence. And we have 0 non-bonded pair to be placed around the central atom. We have 4 sockets, 4 bonded and 0 non-bonded. Parent geometry is tetrahedral, and so will the shape of this be. And that's the shape, as best as I could come up with. The bond angles are going to be all 109.5. There are 4 sockets on the central atom. The sockets contain 4 bonded pairs of electrons. Repulsion dictates all the angles will be 109.5. And that's the H and H bonds, angles. Bonds angles. Okay. Now, so the geometry is tetrahedral. And now we're going to place in the dipole moments, but you could probably guess already that the dipole moments will cancel and that you'll have both symmetry and no polarity. So it is a non-polar molecule. Okay, boron trihydride. All right. Let's just see what the structure might be. And it's going to look like that. Hydrogen, boron, 3. So it's going to look like trigonal planar. Let's see what actually it will be. Well, we have 6. 6 electrons. Well, we have 3 bonds, and there's our 6 electrons. 3 bonds multiplied by 2 equals 6 electrons. And they're hydrogen, so there are none needed, no electrons are needed to complete the valence. So you have 0 non-bonded pairs to to be placed around the central atom. Now, boron is a nonmetal, but it's also a metal. It's a metalloid. Metalloids may contain 6 electrons. A metalloid can be treated as a metal in this particular circumstance. So it's okay. It's going to have 6 electrons, and that's the end of it. So there are 3 sockets on the central atom, 3 trigonal planar. The sockets contain all bonded pairs of electrons. Repulsion dictates that all the angles will be 120 degrees between all adjacent atoms. Boron has only 6 electrons. This is acceptable to the rules because, again, boron is a metalloid. It's not a nonmetal. There's the geometry, trigonal planar or trigonal planar, and the dipole moments will cancel. The dipole moments will cancel. There they are. They cancel. Bond symmetry, yes. Polarity, no. Krypton difluoride. Krypton difluoride. We're going to look at the possible geometry. Well, we'll put linear for now because we have no way of knowing otherwise. We might be able to guess what the geometry is. If you can guess what the geometry is based on prior examples, that's pretty good. So we have 4 electrons in bonds, and we have, how many electrons? So there's 2, right? So there's going to be 12 electrons in completing the valence. So that gives us 12 plus 4 is 16. And we have 6 left over. So that gives us 3 pairs, 3 non-bonded pairs. So the parent geometry is going to be trigonal bipyramidal. And so the shape is going to look like this. And let's read what this says. And you've read this before. There are 5 sockets on the central atom, 2 polar B and 3 trigonal A. The sockets which contain the non-bonded pair of electrons are the trigonal sockets. Repulsion dictates the bonded electrons will oppose each other in the polar sockets, and that's going to be 180 degrees. All right, so what do you think the geometry will be? It'll be linear. Remember, the parent geometry is trigonal bipyramidal, 5 sockets. There's the, Krypton, yes. Krypton has an electronegativity, and the larger noble gases do. So it has symmetry, yes. Polarity, no. It is nonpolar. Okay, let's look at carbonate, -2 charge. All right, so we'll write that as a trigonal planar particle, -2. And that gives us 24 electrons. All right, good. 24 electrons, 3 bonds multiplied by 2. That's 6 total electrons in the bonding for the use for the bonding, and then 18 for the completing the valence. So that's going to be 24 electrons. We're going to subtract 24 from 24, and we will get 0. So we have 0 non-bonded pair to be placed around the central atom, and that will give 3 sockets, 3 bonded, 0 non-bonded. Parent geometry is trigonal planar, and by goodness, it's got to be manipulated a little bit because carbon only has 6 electrons. So we'll make one double bond. That should be easy for you by now. When the central atom is a nonmetal, it must have at least 8 electrons. So 2 oxygen electrons are shared with the carbon. The double bond is treated as a single bond. And because the carbon has 0 non-bonded electrons, the geometry is planar. So it'll be trigonal planar. Okay. And remember, you're going to have, those 2 bonds that are near the 2 bonds, the 2 angles that are near the double bond will be a little bit greater than 120, and the angle underneath will be a little bit less. Okay, so there it is. It says the angle A is slightly larger and angle B is slightly less. We're going to put in the dipoles. So we have bond symmetry and polarity. So we have yes on bond symmetry, no on polarity. Now, here's one. Xenon dioxide, difluoride. A lot of fun. Okay, here we go. Now remember, you could put I'm not really looking necessarily at a lot of the heavy chemistry. You might want to put the fluorines on opposite, opposite the oxygen. That's not what this lesson is about necessarily. So we have 4 bonds times 2 is 8. And I'm just going to let this run to the end. This is, I'll read the notes. But the note should be familiar to you. I'm going to let you read the notes, because you will see that this is very straightforward. All you have to do is follow the rules. So this note should be familiar to you based on past examples. You can probably see the structure already. We've probably done this structure more than any of the other structures. It'll be close anyway. And that concludes it. Okay? No bond symmetry, and yes, we have polarity. It is a polar molecule.